Good morning, sir.
Yeah. So are there any questions, doubts? Anybody has any question, any doubt? Want to ask anything? Okay, then let me start. So today I'm going to start plane stress, plane strain, finite elements. So I'll just give a brief information about that and then finite element formulation. So we are continuing. Oh, it is not writing. So is my screen visible? Hello, hello. Is my screen visible?
No, sir, it is not visible, sir. Sir, now it is visible, sir.
Okay, okay. Yeah. So I'm going to start this plane stress and plane strain elements. Both will be covered in the same formulation. So as you know, I know in basic courses on solid mechanics, you would have done this. So what we are trying to do is we have structure. Of course, the geometry can be anything, but I'm just sketching a rectangle. So let us say we have this rectangular domain x and y is the coordinates and the dimensions are, let us say, this is dimension b and this is dimension a, and this is subjected to, so the whole structure is in xy plane. So its thickness is along z direction, which is along the normal to the screen. So now if this is only subjected to forces which have got only x and y components, so there could be body forces which have got only x and y components, no jet component of force. And similarly along the boundary there could be forces along the x and y direction. So these can be the various forces. So now depending, so the basically the whole structure is in xy plane and the thickness is along the z direction, that is normal to the screen. So and the forces are also acting along the x and y direction. So there are only forces which have only x and y components. So let us say, the simple example you can think of is actually hanging screen. So if you look at hanging screen, so hanging screen, you would see that because of its self weight, the load is in the directions containing the screen plane of the screen, and the so thickness is of course very small in that case. So that is a plane stress problem. So but it could be plane strain problem also, so that depends on the thickness. So if the thickness, let us say, if the thickness if we talk of let us say h, so there are two possibilities. If the thickness is very small, thickness is very small means basically a by h would be a large, would be much greater than 1. So then if the thickness is small, then this problem would be referred to as plane stress problem. Plane stress problem means the sigma zz would be 0, because you see the xy and z is going to be normal to the screen. So the sigma zz and tau xz and tau yz would be 0. Of course, there is a generalized plane stress case where sigma zz is 0 but tau xz and tau yz are non-zero. So that is one possibility. And the second is if the thickness is very high. Thickness is very high means A by H is much less than actually 1. Then this is known as plane strain problem. So we are going to combine these two together. So if you see this kind of a structure of although the surface geometry could be any even it could be irregular geometry, it could be circular geometry, it could be triangular geometry, it could be square geometry, anything. But the loads are in the in plane direction, so the independent displacements. So if we take any point at a location xy, so it is at some position, and then after the application of the forces this point would move to somewhere this location. So this is the initial position of the point and this is final position of the point. So you will see that this point would get displaced by an amount u along the x direction and v along the y direction. And so the entire plate also would get, depending on the situation, it may get displaced like this. So that could be the finally the deformed position of the plate. So if you look at the displacements, so if you look at displacements, so we will have two independent components of displacement. One is u. U is the displacement along x direction. So that is you have the plate and any point on the plate. When you apply the load, the plate deforms and therefore the point which was originally at some location, its current location changes. So that change in the location we are referring in terms of the displacements. So we have u and this u would be function of x and y. This is basically displacement along x. And similarly, we will have displacement v, which will also be function of x and y. That means different points of the plates would have in general different displacements. So this is also function of x and y, and this is the displacement along y direction. So once we have these displacements, then we talk of strains. So if you look at the again independent component of strains, so you will have, I think you would have studied, we have normal strain epsilon xx, which is the rate of change of u, so del u by del x. And then you have normal strain along y direction. So it means that if you take a differential element of length delta x along x direction, so then its change in length per unit original length when delta x tends to 0 is the normal strain along x direction. Similarly, epsilon yy, if you take a line element along y direction of length delta y, and then after the application of load, this length changes. So that change is, let us say, delta v. So delta v upon delta y, the limit delta y tends to 0 is the normal strain along y direction. So this is del v by del y. So these we call as in plane normal strains. In plane normal strains. Why in plane? Because they are in the plane of the structure. The plane in which the structure is lying. So these normal strains are in that plane. So they are referred to as in plane normal strains. And then you will have shear strain. So that is gamma xy. That gamma xy would be equal to del u by del y plus del v by del x. And this we call it as basically the in plane shear strain. So this is in plane shear strain. And this what it means is that in the structure, so if you have initially a line element parallel to no, x and y, so let us say this is delta x and this is delta y. After the deformation, when the plate deforms, so these move and go somewhere here. So now this change in angle, what you have do this angle plus this angle, these two no, sum of these two angles change in the angle from the initial right angle position, you call it as shear strain. And what I am writing here is the engineering shear strain. So no, these are the basically independent components of strains. And then you have the, as I said, the transverse shear strengths are zero. So gamma xz by definition is basically del u by del z plus del w by del x. So in this case, we have said that u is only function of x and y, so it is independent of z. So this is zero, and there is no displacement along the z direction. So this w is zero. So therefore, this whole thing is zero. And similarly, gamma yz would be del v by del z plus del w by del y. Again, as we see here, v is only function of x and y. It is independent of z, so this term would be zero, and this w is zero, no displacement along z direction, so therefore this is also zero. So these two transverse shear strains are zero. These are known as transverse shear strains. So once you have, and why do we need these stresses and strains? So that we can design the structure. Ultimately, you may want to find out how much maximum load it can take, or what is the maximum load it can support. So, or what should be its thickness to support a certain load for a certain material of the plate. So therefore, that is why you need to study these stresses and strains. So then next we look at the stresses. So if you look at the stresses, there are going to be basically normal stresses along the x and y directions. So those are, say, sigma xx and sigma yy. So these are referred to as in plane normal stresses, and you will also have tau xy, that is in plane shear stress. So once, we have also, of course, you will have tau xz is equal to 0 and tau yz is equal to 0. So similar to these transverse shear strains, these are transverse shear stresses. So yeah, once we have these components, then we'll look at stress-strain relation. So what we call as the constitutive relation, or stress-strain relation. So in this, what we are going to assume, as we did earlier, so I'm going to assume that the material is linear, elastic, isotropic. So we are doing, for that case, whatever we are going to discuss. Although I know this can be done for the other materials also, but for the time being, we are restricted to linear, elastic, isotropic materials. So material is linear, elastic. Linear means the relationship between stress and strain is linear, and elastic means it remains within the elastic limit. So if you unload it, it comes back to its original configuration. So linear, elastic, and isotropic. That means the material properties are same in all direction. Isotropic. We are not saying whether it is homogeneous or not. So you of course should know the difference between isotropic and homogeneous. So isotropic means at a given point the properties are same in all directions. In a homogeneous means in a given direction the properties are same in all locations, all points of the body. So that is known as homogeneous body. So now I'm going to talk of, as I started with, plane stress and plane strain conditions. So the main difference comes whether it is plane stress or plane strain in the stress strain relationship. So let me talk of the stress strain relationship or plane stress case. So let us say plane stress condition. And I have already said, so now if you take some point on the plate, so let us say if I take a point over here and take a small square around that, and so the stresses in that. So the stresses are basically, these are the stresses at a point. So you have this sigma xx, and positive normal stress is along the outward normal to the surface. So if the outward normal is along plus x direction, then the positive stress is along plus x direction. If outward normal is along negative x direction, then the positive stress is along the positive x direction, and similarly y. So these are the normal stresses. This would be shear stress. So this is tau xy. So this is what we are talking about. So now when I write the stress strain relationship, so let me first write strain in terms of stress. So if you write sigma xx, sorry, epsilon xx, so no normal strain along x direction epsilon xx. So you would have studied the generalized Hooke's law. So basically now we have stress along the x direction. So because of that stress, the strain along x direction is going to be simply sigma xx divided by Young's modulus. That is stress divided by strain. Sorry, the stress divided by Young's modulus is the strain sigma xx upon E, where E is Young's modulus. But here at the same time there is a normal stress along y direction. So if you are stretching along the y direction, due to that this body is going to contract along the x direction, and that amount of contraction would be the ratio of contraction is going to be equal to Poisson's ratio. So therefore this would be minus sigma y upon E is the stretch along y direction, and multiplied by Poisson's ratio nu will give you the contraction along x direction. And so similarly, let's say there is a normal stress along z direction also. So along the z direction, stress would be sigma zz upon E, and due times this value will give you the contraction along x direction. So ultimately, you see for the normal strain along x direction is sigma xx upon E minus nu into sigma yy upon E minus nu into sigma zz upon E. Here no E and nu are Young's modulus and Poisson's ratio. So E is Young's modulus, as you know, and nu is Poisson's ratio. And for the plane stress case, of course, sigma zz is going to be 0. So we will have no, when I say plane stress case, essentially I am talking of sigma z is equal to 0. So that term is going to be 0. So similarly, if you look at sigma epsilon yy, normal strain along the y direction, so it would be sigma yy upon E. That is the, because if we have a positive stress along y direction, sigma yy, then the strain due to that along y direction is going to be sigma yy upon E. But there is a normal stress along x direction, so that will lead to contraction along y direction. So that contraction would be minus nu times sigma xx upon E. Similarly, minus nu times sigma zz upon E. This will also lead to a contraction, but we are saying for the plane stress case, this is actually equal to 0. So now similarly, if you look at the epsilon zz, normal strain along z direction, so that would be sigma zz upon E, that is stress due to sigma zz along z direction minus contraction due to sigma xx and sigma yy along z direction. So those contractions are due times sigma xx upon E minus due times sigma yy upon E. And you would see that of course this sigma zz is equal to 0. So you would ultimately see that epsilon zz is minus nu upon E times. So you can see that this is minus nu upon E times sigma xx plus sigma yy. So it's not really independent, but it can be expressed in terms of sigma xx and sigma yy. Now if you look at B, what we want to do, we want to do the displacement based formulation. So that means ultimately we want to express know all the equations in terms of the displacements. So rather than writing strains in terms of stresses, we want to write basically the stresses in terms of strain. So if you look at these two equations, so they are relating sigma xx epsilon yy and those epsilon xx epsilon yy and sigma xx and sigma yy. So it is relating these two quantities. So we can solve this equation for sigma xx and sigma yy. So that means express sigma xx and sigma yy in terms of epsilon xx and epsilon yy. So basically solve these two equations for sigma xx and sigma yy. So if you do the solution is straightforward. I think you can do that. So what you can do is, if you want to eliminate, let's say, sigma xx from both these terms, so the first equation you multiply by nu, and then add the two equations. So sigma xx would be eliminated. You can solve for sigma yy, and similarly, you can, if you want to eliminate sigma yy, then the second equation you multiply it by nu, and then add the two equations. So then you can solve for sigma xx. So that solution, if you look at, it will come out as sigma xx upon E upon 1 minus nu square into epsilon xx plus nu times epsilon yy. So now it's a two-dimensional case. So you find that stress sigma xx is no longer simply E times epsilon xx. So here sigma xx is not simply E times epsilon xx, but sigma xx is E upon 1 minus nu square times epsilon xx plus nu times epsilon yy. So you have to keep this in mind, that no, for the 2D case, this is what going to be the stress-strain relation. And similarly, sigma yy would be equal to E upon 1 minus nu square epsilon yy. You will have epsilon yy plus nu times epsilon xx. So similarly, you would see that tau xy would be equal to g times gamma xy, and for isotropic materials, we know that g is E upon 2 into 1 plus nu into gamma xy. So here, of course, g is known as shear modulus, which is related to Young's modulus for the isotropic material what we have talked about. So these are the expressions for stresses in terms of strains. So now, of course, this concept you can also use, experimentally. Let's say you have designed a ship and it is manufactured, and then you want to validate the design. So you experimentally want to measure the strains. So you will have something known as the strain gauges. So electrical resistance strain gauges. You can paste those strain gauges on the critical locations and measure the strains, and then using these relations you can calculate the stresses. So you can do that also. But of course, in the finite element, we are going to do all these calculations numerically. But no, this is useful there also. And many a times it is actually done. The strain gauging of the ship hull or sometimes submarine is done to validate the design. And then it is loaded, and these strains are measured, and then the stresses are calculated. So now ultimately, of course, in the finite element, we want to express everything in terms of matrix vector relationship. So we can put this in the matrix form. So we can say that sigma yy, sigma xx, sigma yy, and tau xy is equal to. Now, if you look at in both these relations, I have E upon 1 minus d square common. So I can take that as common, and then a matrix in between. And this side I can have strains epsilon xx, epsilon yy, and gamma xy. So now if you look at the first relation is epsilon xx plus nu times epsilon yy. So I should have unity here, and I should have nu here, and then 0 here, because gamma xy is not coming over there. And of course, E upon 1 minus nu square is already there. In the second relationship, we have nu times epsilon xx plus epsilon yy. So here we should have nu, so that we get nu times epsilon xx, and here 1, and this is 0. And then this 0, 0. And here we should have ultimately E upon 2 into 1 plus nu. So what we have here is 1 minus nu square. So if we have 1 minus nu by 2 here, so when we multiply this and this, we get basically E upon 2 into 1 plus nu, which is g into gamma xy, gives you the shear stress tau xy. So now we can write this in the symbolic form. So you can show that, no, you can write sigma. Sigma is basically this, and this is the constitutive matrix C, and this is epsilon strain vector, this one. So here C is known as the constitutive matrix. We call now this C as the constitutive matrix. And so this is the stress strain relationship for basically plane stress case. So in plane stress case, sigma zz, tau xz, tau yz are 0, but epsilon zz is non-zero for plane strain. You see, epsilon zz is given by this expression. Now the other case is plane strain case. So in plane strain, basically epsilon, so the thickness is very large. So the body doesn't no display, no there is no relative motion between the points along the z direction. So the epsilon z remains same for the plane strain case. So in plane strain, you have basically no epsilon zz equal to 0, and of course tau xz and tau yz are anyway no gamma xz, gamma yz, tau xz and tau yz are anyway 0. So this is known as a plane strain condition. So from this, what you can actually do. So if you look at this relationship again, we have written actually this earlier. So see epsilon zz is sigma zz upon E minus nu times you have sigma xx upon E minus nu times sigma yy upon E. Now for the plane strain case, where we have a thick body, epsilon zz is actually 0. So this will be equal to 0. So therefore you can express here sigma zz, because corresponding to sigma zz we have strain epsilon zz, and epsilon zz is 0. So we want to express sigma zz in terms of the other two stresses. So you would see that in this case you can write sigma zz is equal to you can cancel out basically this E and this E, because epsilon zz is 0. So you would find that this simply gives you sigma zz is equal to nu times epsilon xx plus epsilon yy. So in case of plane strain, the normal stress along the thickness direction, which is a very large thickness, the stress in that direction is equal to nu times sigma xx plus sigma yy. Now, if you have any doubts, now you can ask in between. Any doubt, and you have any doubts and questions, please ask. So now once you have this, the sigma zz, then you can look at how the expressions for strains epsilon xx and epsilon yy get modified. So now we will have epsilon xx normal strain along the x direction, which is we have written this already this relation sigma xx upon E minus nu times sigma yy upon E, and minus we have nu times sigma zz upon E, and sigma zz is given by this expression, so we get nu square upon E into sigma xx plus sigma yy. So this is what no, you get this relationship. You can take sigma xx common, so you see that we have 1 minus du square into sigma xx upon E, and then the other term we have 1 plus du into du upon E times sigma yy. So these are the straightforward relations. Maybe you would have done in the solid mechanics course, but I am revising that. So similarly, epsilon yy is sigma yy upon E minus nu times sigma xx upon E, and minus we have nu upon E times sigma zz. And sigma zz is this, so we get nu square upon E into sigma xx plus sigma yy. And so if you simplify again, so this you can write basically 1 minus d square into sigma yy upon E, and minus you can write 1 plus du into du upon E into sigma xx. And of course this shear strain gamma xy remains same, that is tau xy upon G, and which would be E upon 2 into 1 plus nu. No, I'm dividing by yeah, let me just write the one G. So G is where no G is E upon 2 into 1 plus nu. So now what you can do again, our aim is in the finite element formulation, because we want to express everything in terms of displacements. So we want to write actually stresses in terms of strains. In these relations, this relation and this relation, you see that the strains are expressed in terms of stresses, but we want to express stresses in terms of strains. So if you solve these two equations, essentially know this equation and this equation for sigma xx and sigma yy. So I put them in the matrix form. So you get sigma xx, sigma yy, and tau xy these two will be equal to, now for the plane strain case, this relationship comes out as E upon 1 plus nu into 1 minus 2 nu, and then inside we have here 1 minus nu and 0 nu 1 minus nu 0 0 0 1 minus 2 nu by 2. The third, no, this term is so that we get G, epsilon xx, epsilon yy, and gamma xy. So what you will notice over here, know that we can write this also in terms of sigma is equal to C into epsilon. So this is sigma, this matrix is C, and this is epsilon. So you would see that there are three independent components of stress and strain. So for both plane stress and plane strain, the relationship is same. Only thing is that C matrix is different. So you see in the plane strain case, this is the C matrix what is written here, and for the plane stress case, this is the C matrix what we have written here. So it's only the form of the stress strain relationship is same for both plane stress and plane strain, and there are only three independent component of stresses, that is sigma xx, sigma yy, and tau xy, and similarly three independent components of strains, epsilon xx, epsilon yy, and gamma xy. So this form is actually the same for both plane stress and plane strain, and therefore the finite element formulation can be done for both the problems. Basically at once, and depending on whether the it's a plane stress problem or a plane strain problem, you use the appropriate constitutive relation, that is C matrix. So either this one or the previous one. And how will you decide whether you should go for plane stress or plane strain? That would depend on thickness. So if the thickness is much smaller compared to the other two dimensions, then it is plane stress case, and the thickness is very large compared to the dimensions A and B, then it is a plane strain case. So once we have discussed this, the next thing is, now I'm not going to derive, although we can derive, but I'm not going to go through the equilibrium equations. Actually, there would be now here two independent unknowns u and v, so there would be two equilibrium equations. But we are going to derive the element level governing equation from the total potential energy functional. So I'm going to write that directly, consisting of strain energy and the potential of the external forces. So now let me write total potential energy. Total potential energy functional. So that I'm going to denote it by I. So as you know, the it will have strain energy part. So integration over volume. And now let me write it for an element, not for the structure as a whole, but I'm writing for one particular element. So as you know, the strain energy is integration over volume half into sigma xx into epsilon xx. But now here we have got two more pairs of stresses and strains. So we will put all of them together. So the strain energy would be sigma xx into epsilon xx plus sigma yy into epsilon yy plus tau xy into gamma xy. So this is, and of course half is there outside, this into dv volume integral. So this is the strain energy. So as you know, this is basically what we are writing is strain energy. So this is strain energy, and then we will have to include the potential of body forces. So the body forces means there could be forces per unit volume. So again we have to integrate over volume. So potential is going to be, because we are assuming that the body forces components mbx and mby are along x and y direction, and the displacement along x and y directions are u and b. So the work done would be positive and the potential would be negative. So we will have Fbx into U plus Fby into V into integration over volume. So this is the potential of body forces. So this term is basically potential of body forces. That is force per unit volume, and then there would be on the boundary of the domain. So like what we were talking about here, doing the boundary. So this is the part of body force, and
User,
these are the, yeah, these are the part of the
so can you please
boundary
repeat the
force.
potential of body forces again?
Yeah, so the potential of body forces, how I'm writing is Fbx is the force per unit volume along x direction. So then now we will have FBX into U into dV will be the basically work done, and the potential is going to be negative. So we have discussed this concept earlier. So it is the same thing. Though Fbx is the force along x direction. So force into displacement along x direction is the work done. Negative of that is the potential. So that is how I have written. Similarly, Fby is the force per unit volume along the y direction. So Fby into dv will be the total force over a differential volume into small v will give you the work done, and negative of that is going to be the potential. So that is how I'm saying this is the potential of body forces. Then you have on the boundary also there are forces acting on the body. Those we call as boundary tractions. So boundary tractions I'm denoting by T and X. So T and X into U plus T and Y into V, and then know if it has got a thickness H into the arc length, that is length along the boundary is ds. So this term is basically nothing but potential of surface tractions on the boundary. So this is the basically where the total potential energy functional consisting of strain energy and the potential of body forces and the potential of tractions acting on the boundary. So as I said already here Fbx is the body force per unit volume along x direction. And similarly fby, b subscript b stands for body and x and y for the direction. By is the body force per unit volume along y direction. And similarly if you look at tnx, this is also actually force per unit area, but we call it as a surface traction. So surface traction, because this is on the boundary, surface traction per unit area. So this is stress like quantity per unit area along x direction, and T and Y is the surface traction per unit area along y direction. Now we want to write ultimately this in the form of product of matrices and vectors. So we can essentially rewrite that integral functional, and additionally we are saying here that stress, strain, displacement, forces and tractions, everything are constant along the thickness direction. They are independent of z coordinate, that is thickness coordinate. So we can explicitly write the thickness integral separately in terms of the thickness. So let me write that since all quantities means stress, strain, displacements, and forces, body forces and surface forces, tractions are constant for the plane stress of plane strain problem. These are assumed to be constant through the thickness. Of course, for the there is a concept called generalized plane stress which is used in plate bending. So there, of course, the sigma xx, sigma yy, and tau xy would find they would be function of z. Then the thickness integration has to be done appropriately. But for the problem under consideration, these are constant through the thickness. Through the thickness. Thickness means z coordinate. Thickness, that is along z direction, which is normal to the screen, the way I have written. So then what you can do, then I can write this I as half, and the volume integral can be written as area integral, area over the element, and then I can put the all the three terms as sigma xx, sigma yy, and tau xy. the three terms in the strain energy we have, we can write it like this: epsilon xx, epsilon yy, and gamma xy. And then volume dV can be written h into dx dy. So this will give you the same thing. No, when you take sigma xx, sigma yy, tau xy transpose, so it will give you same thing: sigma xx into epsilon xx plus sigma yy into epsilon yy plus tau xy into gamma xy, minus you have integration again over the area, and then you have no uv transpose into we have fbx fby. So this will also give you the same thing here, h into dx dy. And the traction similarly minus integration over the volume, that can also be written in the form of matrix and vector. So u and v transpose into tnx t and y, and then h into ds. So this is what you get as the basically the no integral functional. And now what I want to do is, we want to right now this integral functional involves the both stress and strain quantities. So we want to write everything in terms of strain, so that finally strains are written in terms of displacement. So everything is in terms of displacement. So we can write that we know the stress strain relationship. So we can write I is equal to half the integration over area of the element, and then sigma, this is no sigma transpose. So sigma we have said already, now if you we have said no, this sigma is equal to c into epsilon, we have said this. So now if you take no sigma transpose, that would become epsilon transpose into c transpose, and since c is a symmetric matrix, so that would become epsilon transpose into c. So you can write here, this you can write as no epsilon transpose into c. And when we are writing, no, there is another thing called, no, when we write no the stress and strain tensors, they are actually second order tensor, but we are writing in the form of a vector. So this is known as Voigt notation. So when we write it in this form, know the second order tensors, although they are usually written in the matrix form, but when we write in the form of a vector, so we call that as a Voigt notation. Voigt Voigt notation. So we have epsilon transpose into C into epsilon into H into dx dy, minus we have now the again integration over area and the body forces. So those are anyway there as it is, uv transpose fbx and fby, h dx dy, and minus of course the boundary integral. So we have uv transpose into tnx into tny h into ds. So this becomes ultimately your integral functional. So now we have, let me number this. So let me call this as equation number 1. And now we let us go to the finite element formulation. So far we have actually just discussed the basics of any plane stress, plane strain problem. And of course when you solve these problems, so ultimately from the design point of view, you might either be interested in finding out maximum shear stress, or you might be interested in finding out the maximum normal stress, or you might be interested in finding out the von Mises stress. So you should be able to know, you would have studied the relationship how to calculate the maximum shear stress from sigma xx, sigma yy, and tau xy, how to calculate the maximum normal stress, how to calculate the von Mises stress. So you, of course you need those relations from the design point of view. So now let's talk of the finite element formulation. So let me first consider the simplest element. So the simplest element is basically a three-noded triangular element, similar to what we discussed in the heat transfer problem. So this is the element what I'm going to discuss. So the finite element, now it's a 2D element, this is x and y, and the element is a triangle, three-noded triangle. So we have these nodes, all the edges are straight. So these are, let's say, local node numbers, local node number 1, 2, and 3. and the coordinates are no this the coordinates of this are x1 y1, coordinates of this are x2 y2, and the coordinates of this node are x3 y3. And u and v for the plane stress problem, u and v are going to be the primary variables, so there should be degrees of freedom at the nodes. So u1e, v1e, and similarly u2e, v2e, and similarly no u3e, v3e. So these are u1, v1, u2, v2, u3, v3 are the values of displacements u and v at nodes 1, 2 and 3. So this is the element we are going to talk about. So now you see that it's a three noded element. At each node we have 2 degrees of freedom, that is values of u and v, and for the element as a whole we have 6 degrees of freedom. Of course, corresponding to u, there are 3 degrees of freedom, u1, u2, u3. Corresponding to v also, there are 3 degrees of freedom, v1, v2, v3. So next step, as you know, in the finite element formulation is the displacement approximation. So we go for the displacement approximation. So when you go for the displacement approximation, so what do we see? We see we have to look at the differentiability requirement. We have to look at the completeness requirement. We have to look at the inter-element compatibility requirement. So if you look at the differentiability requirement, so in the integral functional, what we have is the strains, and the highest order derivative strains is the first derivative of u and v with respect to x and y. So you can say that the highest derivative of displacement present in the integral functional is first derivative, and therefore no u and v are the primary variables. So whatever we assume, it should be differentiable at least once. That means we can take a linear polynomial in x and y, but it should be a complete polynomial. So therefore we can take u is equal to a0 plus a1x plus a2y. So this is no differentiable once with respect to x, differentiable once with respect to y. It's a complete polynomial. It is geometrically invariant because if we interchange x and y, the form doesn't change. And then also we have a naught u1 a1 a2. They can be expressed in terms of degrees of freedom u1 u2 u3. So no, and of course I will discuss how we satisfy the inter-element compatibility, because we have to not only satisfy at the nodes but along the common edges. So that is what we have to look at it. So this is as far as u is concerned. So similarly, you will assume the approximate solution for v. So let us say that is in terms of another set of constants b0 plus b1x plus b2y. This is the approximation within the element. Why it is so? Because u and v are functions of x and y. So when we are solving a problem, that means we are interested in finding out u and v as a function of x and y. And if we have u and v as a function of x and y, then we can get the strains, then we can get the stresses. And once we get the stresses, we can find out maximum shear stress or one basis stress or maximum principal stress. And then we use that for the designing of the structure. So that is what no, we want to do over here. Now, next thing is we want to express the constants a0, a1, a2, b0, b1, b2 in terms of values of u and v at nodes 1, 2, and 3. So at node 1, you would see that no, u is equal to u1, so u1e is equal to a0 plus a1, and the x coordinate is x1 and y coordinate is y1. And similarly, u is equal to u2e at node number 2, where x and y are x2 and y2. Here you would see that x1, y1, x2, y2, x3, y3 would be known because we will know the geometry. So therefore, coordinates of nodes we will know, but these are unknowns. Unless we solve for, we don't know the displacements. So similarly, this would be a0 plus a1 x2 plus a2 y2. And similarly, u3 will be equal to a0 plus a1 x3 plus a2 y3. So you will see when you look at this alone, the solution is similar to the heat conduction problem. The way we solved for the constants a0, a1, a2, and then express their temperature in terms of area coordinates and the nodal degrees of freedom. So the same thing we can do over here. So similarly, for V also you can do the same thing. The form of equations is going to be same. So we will have V1 at node 1 will be equal to B0 plus B1 into X1 plus B2 into Y1, and V2E will be equal to B0 plus B1 into X2 plus B2 into Y2, and then V3E will be equal to B0 plus B1 into X3 plus B2 into Y3. Same way, no, the solution for this is also going to be exactly same. So now if I call these two as no equations, this as, let us say, equation 2. So now if we express A0, A1, A2, B0, B1, B2 in terms of U1E, U2E and U3 by solving these equation, and B0, B1, B2 in terms of V1, V2, V3 by solving these equations. So similar to what we did for the heat conduction problem, you would be able to write finally that no, so by essentially, let me write the step, and then yeah, I think that would be better. So rather than writing just the result, so now you have to solve for A0, A1, A2, B0, B1, B2, and substitute in equation 2. So this will give us, we will get u is equal to same area coordinates will come what we have defined already. So I'm not going to define that again. So the same area coordinate will be L1 into U1E plus L2 into U2E plus L3 into U3. So you remember L1, L2, L3 are area coordinates. Their expressions are exactly same what we discussed for the heat transfer problem. So similarly, V will be equal to L1 V1E plus L2 V2E plus L3 V3E. So as usual, what we do, we write these in terms of the in the matrix vector form. So we want to write this no, as a basically matrix vector form. So U and V put together will be the no, interpolation matrix H over here. We call this no, H is the same in the first time when I had discussed 1D element. We are using continuing the same nomenclature. No, this is the interpolation matrix H in between, and then the vector of elemental degrees of freedom. Now the now we have two displacements. So usually what we do is the first we write the displacements of no along x and y direction for node 1, then for node 2, then for node 3. So the arrangement of degrees of freedom is usually this manner, that is we have u1e, then v1e, then u2e, v2e, u3e and v3e. So this is vector of elemental degrees of freedom. Now you know u is L1 into U1e plus L2 into U2e plus L3 into U3. So now we want to fill up this matrix. So we have to fill up such a way that when we multiply this interpolation matrix into this vector of elemental degrees of freedom, we should get this expression. So for that we should have L1 here, 0, L2 0, L3 and 0. And then here 0, L1, 0, L2, 0, L3. So if you multiply the first row with vector of elemental degree of freedom, you will get this expression. If you multiply the second row with the vector of elemental degrees of freedom, you will get this expression. So this is what the no interpolation. So you can say that this is UV basically is equal to H into DE. So this is H matrix and this is D vector. Here now you see this H is, we have already discussed this already, so we are using same notation. This is interpolation matrix and DE is the vector of elemental degrees of freedom. Vector of elemental degrees of freedom. Why we call these as degrees of freedom? Because if we know these values, we can we will know the configuration of the element. So that is what is the no, these are the minimum parameters which we need to know the configuration of the element, and that is why these are referred to as degrees of freedom, no, vector of elemental degrees of freedom. So there are now you see this is a 2 by 6 matrix and this is a 6 by 1 vector. So and nodal degrees of freedom are 2. So at each node there are 2 degrees of freedom, displacements along x and y direction, and for the element there are 6 degrees of freedom. That is the x and y displacements of all the nodes. And here you will keep in mind that the L1, L2, L3 are same area coordinates. These are area coordinates we have already discussed. So no, I'm not going to write, but we will be using this. So now to develop the element level governing equations, we have to basically write the strains also in terms of these interpolation matrices. So you know that this epsilon, which is basically epsilon xx, epsilon yy, and gamma xy. This is the vector epsilon, and we know that the epsilon xx is del u by del x, epsilon yy is del v by del y, and gamma xy is the change of angle, which is del u by del y plus del v by del x. So keep in mind here that here is the derivative of u, well, u is the displacement along x. So in the normal strain you have del u by del x, same displacement in the same direction, del v by del y, the displacement along y, and derivative with respect to y. But in the shear strain, engineering shear strain gamma xy, there are cross derivative, a derivative of u with respect to y and derivative of b with respect to x. So these cross derivatives are there. So you would be able to see here that epsilon would be, then we want to write it in the matrix form. So when you want to write it in the matrix form, so you have to write no in terms of course one side you have to have the vector of elemental degrees of freedom u1e, v1e, u2e, v2e, u3e, and v3e. And you will see that this degrees of freedom vector, we will always write a vector, but the interpolation matrix H and the strain displacement matrix B are there in general rectangular matrices. So you know first term is del u by del x, and del u by del x, if you see, is no going to be coming from this expression. So del u by del x would be del L1 by del x into u1e plus del L2 by del x into u2e plus del L3 by del x into u3. So the same we want to write in the matrix form. So here you will have del L1 by del x 0, del L2 by del x 0, and del L3 by del x 0. So that when you multiply this row with this vector, you will get actually del u by del x. And then second term is del v by del y. So 0, we will have del L1 by del y 0, del L2 by del y 0, del L3 by del y. And if you look at the gamma xy, so let me write that. So gamma xy is del u by del y plus del v by del x, and del u by del y then would be del L1 by del y into u1e plus del L2 by del y into u2e plus del L3 by del y into u3e plus del v by del y. So that is del L1 by del x into v1e. Now it's v derivative. So v1e del L2 by del x into v2e plus del L3 by del x into v3. So now when we want to put this in the matrix form, so you see the coefficient of u1 is del L1 by del y. So here I will write del L1 by del y. The coefficient of v1e, which is going with this term, is del L1 by del x. So I will write here del L1 by del x. And then similarly, coefficient of u2 is del L2 by del y. Coefficient of v2 is del L2 by del x. Coefficient of u3 is del L3 by del x, and coefficient of b3 is del L3 by del sorry, this is x, this is y, and this is x. So yeah, this is what you have the strain displacement matrices. And so now if you look at ultimately now this relationship, if you look at, we can say that epsilon would be equal to b into de. So this matrix is basically b. Now you see strain is a 3 by 1 vector. This strain displaced matrix is 3 by 6, and this vector is a 6 by 1 vector. That is already d. We have B we have already defined. So you see this is 3 by 1, this is 3 by 6 and 6 by 1. So the matrix vector multiplication is consistent. And you will see here that when you look at now B, so the derivatives of these coordinates we have already written. So I think yeah, let me write one. So so if you look at now the B and the derivatives are the shape function. So let me write B. So if you remember those yeah, yeah, the relations we have written, so the B's are same what we have defined, no, L1, L2, L3. So whatever we defined for the temperature case, no, so the same is going to be applicable here. So let me just take out the relations from there. So yeah, I don't remember. So yeah, so we have basically, if you look at the relations we had was del L1 by del X we had derived. Del L1 by del X was 1 upon 2 AE into x3 minus no sorry y2 minus y3, and del L1 by del Y was 1 upon 2 AE into x3 minus x2. So now if you look at, I will just write those relations which we had done earlier. So del L1 by del X is basically was, no, you remember in the heat conduction problem we have done this, where A is the area of the element. This was Y2 minus Y3, and del L1 by del Y was 1 upon 2 AE into x3 minus x2. So, and similarly, know the other relations. So, no, for L2, L3 in the cyclic order, you can write the way I had explained earlier. So, if you look at now B matrix, if you look at, so 1 upon 2 AE can be taken common. And then if you look at over here, what you will have is del L1 by del X is now Y2 minus Y3. And then, of course, we will have 0. And then we will have Y3 minus Y1. Then again 0. And then we will have Y1 minus Y2 and 0. And similarly, no, the second row would be in terms of y derivative. So this will be 0, and this would be x3 minus x2, and then 0, and then we will have x1 minus x3, 0, and then we will have x2 minus x1. And this would be derivative with respect to y. So we will have x3 minus x2, y2 minus y3, and then x1 minus x3, and y3 minus y1, and x2 minus x1, and y1 minus y2. So this is going to be actually your B. So for the three noded triangular element, you will see that this is actually constant. Constant in the sense it is independent of x and y. It now know the x1 y1 x2 y2 x3 y3 are the nodal coordinates, they are known quantities. So you would see here that the B matrix is constant. Now this B matrix, you can say that is constant. A constant means independent of x and y. In this case, for the three noded triangular element, this is independent of x and y. X and y means variable x and y. Of course, it is in terms of nodal x and y coordinates. So independent of x and y. So now that means when you look at the strain, epsilon is equal to B into dE. So when you look at this epsilon, which is B into dE, dE is anyway is the constant quantity, that is values of displacements at node point. So this will give you the constant strains within the element. So based on this, what we will get is the constant strains within the element. Constant strains within the element. So therefore this element is also known as constant strain triangle. Constant strain triangle, and abbreviated as CST, constant strain triangle. So yeah, this is what we have. And now if you we want to develop the element level governing equations. So for the element level governing equation, next is once we have these interpolations, then we go for the element level governing equations. Actually, you would notice that if you study formulation of one element nicely, I mean, you understand all the concepts, the involved, then all the formulations are exactly same. See, we are doing the same thing. No, we first look at the displacements, then we look at the strains, we look at the stress strain relation, and then we either look at the no differential equation, weak form integral functional, or directly the total potential energy functional, and then we assume the approximate solution, substitute in the integral functional, and get the element level governing equation and assemble it. And that is the power of this finite element method, and that is why there are so many packages. What I had told at the big, I think the in the lecture when I had started finite element, so there are so many packages, so easily you can do the design and analysis of very complex structures, like no complicated submarine structure, the entire structure or part of it, or the hull, ship hull, or the no the propeller alone, or the entire shafting system, or the piping system. Anything you can analyze using the same set of formulation. No, only thing is when you do those analysis, you'll have to understand that what elements to use, and to use those, what element to use from the software. That knowledge comes if you know the theory behind the each and every element, what are the assumptions made, how it is formulated, and then you will be able to do the analysis using, of course, for the complex problem you will have to use packages. You cannot do those problems manually. Of course, simpler problem, if you are let's say in a submarine or a ship, you have a piping system and you want to design the support of a piping system, that definitely the support can be modeled as a beam, or it can be modeled as a plane stress problem, and you can idealize and model that and do the analysis manually also. But for complex problems you will have to use the softwares. So what we are discussing over here is mainly the theory behind the the finite element formulation, and of course some example problems which are kind of applications. But real applications have to be done actually using the softwares. So now coming to the element level governing equation. So we substitute whatever we have done. We substitute in the integral functional. So if you look at now I is half integration over area, and then we had epsilon transpose. So epsilon transpose would become no your D transpose into B transpose into C, and then again we have epsilon, so epsilon B, and into you have this DE, and then you have the h into dx dy, minus integral over again area, and then we have ub transpose. So that would give you basically d transpose into h transpose into this fbx fby h dx dy. Then we have boundary integrals, so integration over the boundary, and then we have UV transpose, which would give us D transpose into H transpose into TNX, T1Y, HDS. So this is what you have. And now what we can do, we take the, if you look at over here, so we can take this D transpose common on the left hand side and this D on the right hand side. So we could be, we can write that as half, and D can be taken out of the integral because it is independent of x and y. Of course, for this problem, B is also independent of x and y, but in general, this could be function of x. This is only for this particular element. So we have half, and then we can write here, this D transpose. So you can write I equal to half D transpose integration over area, and then we have B transpose into C. And depending on whether it is a plane stress problem or plane strain problem, you will use the appropriate C. C is a 3 by 3 matrix, but its expression in terms of E and nu is different for plane stress and plane strain problem. So B into H into dx into dy, and this is actually your element level stiffness matrix we will have into dE. And then we have this external load vector, so that also we can write minus no d transpose, and then we can have integration over area, and then we have H transpose into fbx fby h dx dy, and then we have the last term minus again d transpose, and then the boundary integral, and we have now again H transpose tnx tny, and we have H into ds. So this is your I, and then you now you see this we call as the element level stiffness matrix Ke. This one we call as the external load vector F external for the element, and this one we call the internal load vector F internal for the element. So ultimately you would be able to say that I is half into dE transpose into Ke into dE minus dE transpose into F external for the element minus d transpose into F internal for the element. So there is a minus sign here. So this is I, and now this is same as what we did for the first element, truss element, 1D element. So you would see that the element level governing equation will be equal to delta I for equilibrium. So that is solution of original differential equation, equilibrium equation is same as no delta I equal to 0. So this will give you the element level governing equation. So we have already derived. So how the steps from here to element level governing equations is the same steps we have done earlier. So I'm not repeating those. So you get the element level governing equation as KD is equal to F external for the element and plus no F internal. Why we are calling this as F internal, the boundary integral? Because in general, when we are talking of elements, so element would be connected to other elements to its sides, adjacent sides. So there you will find that one element would be exerting force on the other element. So this is actually coming from that, and that is why we are calling this as internal load vector. So now here I have already defined where no Ke, the element level stiffness matrix, Ke is nothing but integration over area of the element, and then you will have no B transpose into C into B into H into dx into dy. And if you see the size, this is going to be 6 by 6. This is B transpose is 6 by 3. This is 3 by 3. And this is 3 by 6. So ultimately it would be 6 by 6. And now if we assume that this constitutive matrix C and thickness H are constant within the element, that is they do not change within the element, no, that is thickness is same throughout the element, a particular element, thickness is H is same, and the properties Young's modulus and Poisson's ratio do not change within the element. So C will also not change within the element. So for this particular three noded triangular element, we have already shown, I have already shown that B is constant. So this entire thing then can be taken out of the integral sign. So then you will have integral over area A dx dy, and that will give you the area of the element. So therefore ultimately you can write this will be equal to AE into H into B transpose into C into B, because the B transpose CBH can be taken out of the integral. So you can take say on the right hand side. So left hand side we will left with integral over area dx dy, that will simply give you area AE. So it would be AEH B transpose CB. This is going to be the stiffness matrix provided H and C are constant within the element, constant within the element, within the element. If they are not constant, then of course you have to multiply and do the integration as it is illustrated here. So this is the element level stiffness matrix, and similarly the external load vector is of course the integration over area, and we have now H transpose into this body force FBX and FBY, and then H dx dy. And you keep in mind H is a 2 by 6, its transpose is going to be 6 by 2, and this is going to be 2 by 1. So ultimately this is going to be a 6 by 1 vector, that is 6 rows. Of course, because here H is not constant, H is a function of x and y. So the integral has to be carried out accordingly. You have to put the values of L1, L2, L3 as a functions of x and y, and then you have to carry out this double integral. And similarly, F internal for the element will be equal to integration. No, it's a boundary integral. So that is integration along the boundary. So integration along the boundary, we will have again H transpose into T and X and T and Y, and then we have H into ds. Again, you see this is 6 by 2, it's transpose, and this is 2 by 1. So therefore, this is going to be a 6 by 1 vector. So yeah, this is what you have. Now the element level governing equation for the three-noded triangular element, plane stress, plane strain element. So no, when you want to, as I was talking about, no, if you have support in a pipeline in the ship or a submarine, you will have piping. So I think you would have seen that. So there are many pipelines, and the pipelines are supported at some intervals, and those supports, no, if the cross-sectional dimensions are comparable to length, at least one dimension, then you can model them using this plane stress plane strain element, because the loading is in the no the major dimension, in the plane of major dimensions. So they are ideally can be modeled as plane stress plane strain problem as a bracket for supporting a piping. So now I just give you a homework problem, so you try. I will because the solution is similar to what we have discussed for the heat conduction problem. So this example is similar to that, but you have to try. So this is a homework example. That means you have to do that. So the problem is like this, that you have a no, it can be a square or a rectangular plate, is really doesn't matter why I have taken as square, because no the coordinates become simpler, so you can easily do the solution, although it can be a rectangular plate, and that would be the case in case of piping support in a submarine or a ship. So you have say the dimensions as 2 meter over here. Recently we were actually doing one design of a piping system for the pump in ship. We were doing that design tied in the department. So we had a piping where there were many supports. Of course, no, because we wanted to model the problem as a whole, so we had to use 3D finite elements. But ideally, those the pipings could have been modeled as beam elements, and the supports could have been modeled as plane stress and plane strain elements. So maybe and in some class, I will show you at least how those analyses are done, so that you will have some idea. So this is 2 meters, and let's say the Young's modulus is material is steel. So the Young's modulus is 200 gigapascals. Poisson's ratio is, let us say, 0.3 nu, and the thickness is, let us say, 2 mm, so 0.002 meters. So it is a plane stress problem you would see, and there are no body forces, so FBX and FBY are 0. And let us say on this edge there is a force per unit length, so that means thickness is already multiplied. So if the thickness is already multiplied, then in the internal force you don't have to take that h. So this is force per unit length, so thickness is already multiplied. So this is 20 newton per meter is the force, and let us say there is a force in this direction also. So these are the boundary forces basically. So this is, let us say, 10 Newton per meter. This is also force per unit length. That means thickness is already multiplied in this. So you have to model this. So you can use two triangular elements. Although no, for the convergence point of view, we might have to use more number of elements. But as a manual solution, I am saying that no, you model this using two elements and then find out, let us say that it is fixed here. So this is fixed here. So if you model using two triangular elements, you can take the same way, the way we did heat transfer problem. So these will be the nodes. So this is node 1, this is node 2, this is say 3, and this is node 4. And you model this from here to here. So let us say this is element 1 and this is element 2. So essentially you have to say for each element you have to get the stiffness matrix, which would be a 6 by 6 matrix, and fbx and fby are 0 for both the elements. Here no, fbx is equal to 0, fby equal to 0. Only these boundary forces are there. So you have to calculate, and it's similar, the calculations are similar to the heat transfer problem. Then assemble and solve for the displacements at node 2 and 4. So you have to find out u2 v2 u4 v4, because two displacement at node 2, two displacement at node 4. So model using two triangular elements, model using two triangular elements, triangular elements, and find u2 v2 u4 v4. Of course, one can also calculate strain at any point, stress at any point within the element, but I'm just giving you this as a homework problem. So yeah, I think this is where I want to stop. And now if you have any questions and doubts, you can ask. Yeah, so anybody has any question or any doubt you want to ask, whatever we have discussed today? You must solve this homework problem. That is very, very important. Okay, so if there are no questions and doubts, I am stopping. Thank you all for your attention. Thank you very much.